Hello everyone, myself Dr. J. Srinivas, Senior Assistant Professor, Mathematics. In this video, we will exploring the fundamentals of probability, a key concept in mathematics with application ranging from data science to real life decision making. We will start from the basics like samples, space and events, and then go all the way to Bayes' theorem, one of the most powerful tools in probability. So in this video, we will learn sample space, events, axioms of probabilities, conditional probability, and Bayes' theorem. Now, we begin with random experiment, which is any process whose outcome is uncertain but from the known set of possibilities. A random experiment is an action or process that leads to one outcome from a set of possible outcomes, but the exact outcome cannot be predicted in advance. The outcome is determined by chance, even though the set of possible outcomes is known. For example, if you toss a coin, there are two possibilities. Either you will get head or tail, but we cannot predict which one. Similarly, if you throw a die, there are 6 outcomes. Either you will get 1, 2, 3, 4, 5 or 6. But exact outcome is unknown. Clear? Now sample space and events. Now sample space, it is denoted by S and is the set of all possible outcomes of an experiment. Experiment in the sense random experiment. For example, tossing a coin, S is equal to H comma T, that is either head or tail. Throwing a die, the sample space S is 1, 2, 3, 4, 5 or 6. Similarly, tossing of 2 coins simultaneously, then sample space is head head, head tail, tail head or tail tail. And throwing a pair of dice, there are 36 possible outcomes, and those are 1 1, 1 2, 1 3, 6 5 up to 6 6. Then event. Event is a subset of sample space. So in tossing a coin, sample space is H and T, but getting head is event. In throwing a die, sample space is 1, 2, 3, 4, 5, 6, but getting a one number, that is 2, 4, 6, is an event. And each outcome is called an elementary event. H is elementary event, T is elementary event. Similarly, 1, 2, 3, 4, 5, 6 are elementary events. Now next, let us classify events. This helps us apply appropriate probability rules. Here we have exhaustive events, mutually exclusive events, equally likely events, and simple events and compound events. Now exhaustive events are nothing but the set of all possible outcomes of random experiment. A set of events are called exhaustive if at least one of them necessarily occurs when the experiment is performed. Also, the union of all these events constitute the sample space of the experiment. So for a die roll, events 1, 2, 3, 4, 5, 6 are exhaustive. Now, mutually exclusive events. In short, no two events can happen at same time. Two events are mutually exclusive if they cannot happen at the same time. So getting 2 and a 5 in a single die roll, these 2 and 5 are mutually exclusive. Either you will get 2 or 5, not both. Equally likely events. So what is equally likely events? All outcomes should have same chance of occurrence. Events that have same chance of occurring, in other words, no one event is more likely to happen than another. When a die is rolled, there are 6 equally likely events. Similarly, when you toss a coin, there are 2 equally likely events. Simple event, an event that consists of single outcome, that is elementary event, are called simple event. Compound or composite event, an event that consists of more than one outcome. For example, getting an even number when a die is rolled, that is 2, 4, 6. So this event is compound event. It consists of 3 simple events. Now we define probability. Now what is probability? Probability is a measure of the likelihood that a particular event will occur. It quantifies uncertainty and is used to make prediction based on the known data. So what is mathematical definition of probability? If all outcomes in a sample space are equally likely, the probability of an event, what is event? It is subset of sample space. The probability of an event A is defined as the number of favorable outcomes to event A by total number of possible outcomes, and it is denoted by P of A, that is probability of event A. So, if there are n mutually exclusive equally likely events in a sample space and m events are favorable to event A, then probability of A is m upon n or m by n. Since m and n are positive numbers, ratio is positive. And since the favorable are less than or equal to exhaustive events, so ratio is less than 1. So probability of any event is greater than 0 or less than 1. That is inclusive, equal to 0 and equal to 1. In rolling a die, the probability of getting event A consists of 2 elementary events 1, 5 is 2 by 6, because the sample space S consists of 6 elements 1, 2, 3, 4, 5 and 6. So n is equal to 6 and event A consists of 2 elements, that is n of A, which is m, is equal to 2. So probability of getting this event A is 2 by 6 and in simplest form it is 1 by 3. The probability, second example, probability of getting a numbered card when a card is drawn from the pack of 52 cards. Now the number cards are 2, 3, 4, 5, 6 up to 9 and each has 4 different cases. So total number of number cards are 36 and total cards are 52. So probability of getting numbered card is 36 by 52 and in simplest form it is 9 by 13. The probability of getting sum of 7 when 2 dice are thrown is 6 by 36, because when 2 dice are thrown, the number of elements in sample space are 36 and these 36 events or elementary events are 1, 1 to 6, 6. So these are the number of exhaustive equally likely events. Now, what is event A? Getting sum 7. So the favorable events are 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So these are the favorable elementary events of sample space of getting sum 7. So there are 6 favorable events and 36 exhaustive events. So 6 by 36 is 1 by 6 is probability of getting sum 7 when 2 dice are thrown. Now we define the axioms of probability. There are 3 basic axioms of probability. The first one, For any event A, probability of A is greater than or equal to 0. Second one, probability of sample space S is 1, that is P of S is equal to 1. And third, if A and B are disjoint events, that is mutually exclusive events, then probability of A union B, union stands for OR, that is probability of A or B is equal to probability of A plus probability of B. This is for disjoint events only. S is called certain or sure events, and its complement, that is null set, is called impossible event. So probability of S is 1 and probability of its complement, that is null set, is equal to 0. Now using these axioms, we derive some important elementary theorems. Now for any event A, the probability lies between 0 and 1, inclusive, that is equal to 0, that is impossible event, equal to 1, certain event. Probability of A complement is equal to 1 minus probability of A, where A prime is the complement of A, that is event of not happening A. And if A and B are any two events, they are not disjoint, any two events, then probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. And one more elementary theorem is probability of A minus B, that is only A not B, is equal to probability of A minus probability of A intersection B. Now, what is the probability of getting 7 when rolling a fair 6-sided die? So when you roll a 6-sided die, then sample space S consists of 6 elementary events. Then what is probability of getting 7? It is impossible. So what is probability of getting 7? It is 0. This event is called impossible event. Now what is the probability of getting a number less than 7 when rolling a fair die? Again, the sample space S consists of 1, 2, 3, 4, 5, 6. So probability of getting number less than 7 implies each and every elementary event is favorable. So its probability is 1. So in first one, probability of A is 0, and here in second case, probability of A is 1. So in first case, A is called impossible event, and in second, A is called certain event. Next, if the probability of rain tomorrow is 0.7, what is the probability that it won't rain? That is complement. And we know that probability of A complement is 1 minus probability of A. And here given probability of A is 0.7. So 1 minus 0.7 is 0.3. The last one, in a class 40% like math, 30% like science, and 10% like both. Find the probability that a student like math or science. So here given probability of M is equal to 0.4, that is 40%. Probability of S is, probability of science, don't get confused, it is not sample space. Science, probability of S is 0.1. Probability of their union, like both, that is A intersection B, or in this case M intersection S, is equal to 0.1, and here it is 0.3. So probability of M is 0.4, probability of S is 0.3, and probability of their intersection is 0.1. Then find probability that a student likes math or science. So R stands for union. Then by using third elementary theorem, that is probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So probability of M union S is equal to 0.4 plus zero point 0.3 minus 0.1, that is 0.7 minus 0.1 is equal to 0.6. Now, conditional probability. Sometimes we want to find probability of one event given that another has already happened. This is called conditional probability. So what is conditional probability? One event happens after the happening of another. A conditional event refers to probability of one event occurring given that another event has already occurred. So this conditional probability is also known as probability on reduced sample. Why it is reduced sample? We consider the sample or the number of elements in first event as sample space, and then from we consider only those elementary events which are favorable to second event. That is, if A is first event and B is second event, that is B is happen after the happening of A, then B slash A is called conditional event, and its probability or probability of A slash B is probability of A intersection B divided by probability of B, that is happening of A after the occurrence of B. So here the event B acts as a sample space of A. So first consider event B, and from that the events favorable to A. That's why probability of A slash B or A upon B or A by B is equal to probability of A intersection B divided by probability of B. That is number of elements in A intersection B divided by number of elements in B. Now, what is the probability that both coins show heads given that the first coin show heads? So when the two coins are tossed simultaneously, sample space S consists of 4 elementary events. That is, one is HH, then HT, TH, and TT. So this is the sample space. Now consider event A as the first coin shows head. First coin shows head. So favorable events are HH and HT. And if you consider the event B as showing both the coins head, both coins show head, then the probability of B slash A is 1 by 2. Now this one elementary event A is favorable to B. That is, second coin shows head. So probability of B slash A is equal to 1. That is, probability at both coin shows head given that the first coin show heads. Now in a class of 100 students, 60 passed in math, 50 passed in science, and 30 passed in both math and science. What is the probability that a student passed science given that the student passed math? So your given data is probability of M is 6 by 10. Probability of science is 5 by 10. And probability of M intersection S is 3 by 10. That is 60 by 100, 50 by 100, and 30 by 100. So find probability given that student passed math. So first event is M. Then find the probability that student passed science. So probability of S by M. So what is probability of S by M? Probability of S intersection M by probability of M. That is 3 by 10 divided by 6 by 10. That is 3 by 6 or 1 by 2. Now from 60 student who's passed in math, the 30 belongs to science also. So 30 by 60 is 1 by 2. A die is rolled once. What is the probability that the number is even given that it is greater than 2? So when a die is rolled, what is sample space? It consists of 1, 2, 3, 4, 5 and 6. Now if you consider event A as the elementary event greater than 2, then the favorable events are 3, 4, 5, 6, 7. Sorry, 6. 3, 4, 5, 6. And from this 3, 4, 5, 6, find the probability that the number is even. So there are only two elementary events, 4 and 6. If you consider B as getting even number, then probability of B slash A is again 1 by 2. There are two elementary events in A which are favorable to B. So therefore intersection is 2. Possible elements in A are 4. So 2 by 4 is 1 by 2. Independent events. Two events are independent if the occurrence or non-occurrence of one does not affect the other. That is, in short, probability of A slash B is probability of A, or probability of B slash A is equal to probability of B. That is, A is not depend on B nor B is depend on A. So by using conditional theorem or conditional probability, we have conditional probability as probability of A slash B is equal to probability of A intersection B divided by probability of B. But when A and B are independent events, this probability of A slash B is probability of A. Then we get probability of A intersection B is equal to probability of A into probability of B. It is known as multiplication rule of probability. Now tossing two coins. Event A, first coin shows head. Event B, second coin shows tail. These two events are independent. Similarly, drawing cards with replacement. Remember, with replacement. Event A, first card is heart, then place it back with replacement because then second card is spade. Then these two are independent event. But if the same experiment of drawing cards with replacement, then these two events are not independent events, because for drawing the second card there are only 51 possibilities. Clear? So these two are different events. One is drawing cards with replacement, then A and B are independent. Drawing cards without replacement, then the events are dependent. Now, the law of total probability. The law of total probability is used when an event can occur through multiple disjoint paths. It combines probability from multiple cases to find the overall probability. So in short, if S is the sample space, B1, B2, B3 up to Bk are partitioned events, that is disjoint sets. So this is B1, B2, this is B3, this is Bi, this is BK, this is BJ, and so on. So if you observe this particular figure, B1, B2 up to BK, these events are partition sets of sample space because there is no common element between these two. And if you find their union, then you will get sample space. So what is partition in short? Bi intersection Bj is equal to null set whenever I is not equal to j, and union of all Bi where I takes the value from 1 to k is equal to S. So if B1, B2, B3 up to Bk is partition of sample space S, then for any event A, so this is event A, this circle is event A, we have probability of A is equal to summation of probability of A intersection Bi, where I takes the value from 1 to k, or in terms of conditional probability, A intersection Bi can be written as probability of A slash Bi of probability of Bi. This theorem is called law of total probability because event A is part of B1, part of B2, part of B3, and part of Bk, and union of all these is event A. So probability of A is equal to summation probability of A intersection Bi. Now see here, the factory has two machines. Machine A produces 60% of the items, machine B produces 40% of the items. 2% of A items are defective, 5% of B items are defective. What is the probability that randomly selected item is defective? So what is given data? Probability of machine A is 60%, that is 0.6 or 6 by 10. Probability of B is 40%. Remember, probability of A plus probability of B must be 1 because it is partition set. Now, if you consider D as defective item, then probability of D slash A, that is from machine A, is 2%, 0.02. And probability of D slash B is that is 0.05, that is 5%. And if you choose randomly one item, then find the probability that it is defective item. So what is probability of defective item? First consider machine A and then from that defective item plus machine B and from that defective item. So it is 0.6 into 0.02, 0.4, 0.05. So it is 0.012 plus 0.020. So it is 0.032. Clear? Now one more example. 3 hospitals treat a disease. Hospital A treats 50% of the patients. Hospital B treats 30% of patients and hospital C treats 20%. So probability of A is 0.5, probability of B is 0.3, probability of C is 0.2. If you add these three, then you will get 1. So implies A, B, and C are partition sets of sample space. The probability of recovery of each hospital is 90%, 80%, and 60%. So if you consider R as the event of recovery, then probability of R slash A is 0.9, probability of R slash B is 0.8, and probability of R slash C is 0.6. So what is the probability that randomly chosen patient recovers? So probability of R is 0.5 into 0.9, 0.3 into 0.8, 0.2 into 0.6. So first consider hospital A, and from that recovery rate. Then consider B, recovery rate from B. Then C, so it is 0.5 into 0.9, 0.3 into 0.8, 0.2 into 0.6. Now finally, Bayes' theorem allows us to reverse conditional probability. It helps update beliefs with new evidence. So what is Bayes' rule? Again, if B1, B2 up to Bk is partition of sample space, then for any event A, so what is Bayes' theorem? What is different between law of total probability and Bayes' rule? In law of total probability, we find probability of A. And in Bayes' rule, we find probability of Bi slash A. That is, this particular event A is with respect to Bi. It is from Bi. So this probability of Bi is given by probability of A slash Bi into probability of Bi divided by probability of A. Again, the proof is very simple. Probability of Bi slash A by conditional probability, it is probability of Bi intersection A divided by probability of A. And by using again conditional probability, probability of Bi intersection A can be written as probability of Bi into probability of A by Bi divided by probability of A. So this is Bayes' theorem. Now, a factory has 3 machines. Machine A makes 50% of the items with the defective rate of 2%. Machine B makes 30% with the defective rate of 3%. Machine C makes 20% with the defective rate of 5%. An item is selected at random and is found to be defective. What is the probability that it comes from machine C? If you observe, machine A makes 50%, machine B makes 30%, machine C makes 20%, and the defective rate is 2%, 3%, and 5%. So, probability of A is 0.5, probability of B is 0.3, and probability of C is 0.2. Probability of D slash A is 2%. Probability of D slash B is 3%. And probability of D slash C is 5%. So item is selected at random and is found to be defective. So item is selected and it is found to be defective. What is the probability that it comes from machine C? So probability of C slash D or C by D. Now to find this probability, use Bayes' theorem. So what is Bayes' theorem? Probability of C slash D is equal to probability of C into probability of D by C divided by probability of D. And find this probability of D by using law of total probability, that is 0.5 into 0.02, 0.3 into 0.03, 0.2 into 0.05. So this is probability of defective items, and then probability of this if defective item from machine C is probability of C into probability of D by C divided by probability of D. And second example on Bayes' theorem, 70% of student for an examination, 90% of the student who study pass, 30% of the student who do not study also pass. A student passed in examination, what is the probability that they had studied. So if there are 100 students, 70% of the students study for an examination. So A is equal to 70, or probability of A is equal to 70%. B is 30%. That is, student do not study for examination. If you consider, this is probability of student pass. If you consider student pass, that is C, by A is equal to 0.9, and probability of C by B is equal to 0.3. So a student passed the examination. What is the probability that they had studied? So find probability of C A slash C. So probability of A slash C is probability of A into probability of C slash A into probability of C. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.